All right, hello everyone. Let's consider a really simple differential equation. The one I'm going to discuss now is the derivative of y with respect to x is equal to 6x. Now, it's pretty simple, and we have already seen how to solve this, right? We have already seen it's really basic. You have the derivative of y with respect to x is it's 6x. It's some function of x. So if we want to find y itself, okay, we just need to take the antiderivative, right? We just need to take the antiderivative of this side, okay? So y is going to be the antiderivative of the right side, which is 6x. So this is gonna equal, we're taking an indefinite integral, so 6x, raise the power by 1, divide by 2, you get 3x squared, okay? And since we're taking the indefinite integral, we're gonna have an arbitrary constant. So we got our solution. Y is equal to 3x squared plus c. All right, that's all fine and well. But now what I'd like to do is, I'd like to consider solving this in a slightly different way. Obviously, we're gonna get the same answer, but I just want to consider solving it in a different way, and we'll see later why. Now, we have, again, I'll write that equation again. So what do we have? We have derivative of y with respect to x is equal to 6x. All right. Now, what I'd like to do is multiply both sides by, dx. Okay, multiply both sides by dx. And if I do that, what happens is, so derivative of y with respect to x, I'll write that here. I'll write 6x here. Now, I'm going to multiply dx, okay, an infinitesimally small change in x on both sides. So dx here. Actually, let's use the dot. That's a bit needed. And a dx here, right? And a dx here. So, what do we get? What do we get after this? Well, the right hand side, it's not really uh, anything complicated. It's not really something that can be simplified now, any further. So it's just 6x multiplied by dx. So we'll just leave it like that. But the left hand side, however, what do you have here? We have dy by dx, the derivative of y with respect to x, multiplied by an infinitesimally small change in x. Okay, so there's a couple of ways you can think about what this is, and what basically happens here. A lot of you might have seen something like this in a past differential calculus course, something like this. So you have, let's see, change in x, so call that dx, and first I'll label dy. So for the change in x, okay, in on your graph for change in x of dx, you have a change in y of dy. And so basically this segment, this segment of the tangent, okay, to the graph is gonna have a certain slope, right? Call that m. Well, so what is dy? dy has to be equal to, the slope multiplied by dx, right? By definition, m is your rise divided by your run. And if you multiply that by your run, you should be getting your rise, right? Okay. And, according to this diagram, and even according to the definition of differentiation itself, whether you use the limits one or just rely on this diagram, what is m? M is obviously, the slope here, the slope of the tangent here, right? So whether you go by this triangle or go by the formal definition, m is definitely dy by dx. Okay, so what you're gonna have here is dy by dx multiplied by dx is equal to dy, right? Is equal to dy. So either way, I'd like to think about it. And honestly, most of the time when you just want to solve differential equations, most of the time don't really want to think about this too deeply. So, this is what is commonly done. So you just think about it as, dy by dx as a fraction, although it's not really a fraction. And we just say, okay, so the dx's cancel out. So what we have here is dy, right? We have here is dy. This is going to be equal to 6x, 6x, actually, let me keep a gap here, dy, and this is going to be equal to 6x dx, right? 6x dx. Now, I have dy on one side, I have 6x dx on another side. let's take the integral of both sides. Let's take the integral of both sides with respect to these differentials. Okay, now I'd like to mention that those of you who are a bit bothered by the slight lack of rigor in these last two steps, do stick around till the till the end. I'll explain why this formally works. All right, but let's move on. So if you take the integral of both sides, the integral of 1 dy, 1 dy is gonna be this y, and the integral on this side, 6x dx, as we saw, this is 3x squared. Now about the constants, you might have noticed, and this is something, this is an issue that I avoided talking about before. But when you take the indefinite integral, you need to take it on both sides. Okay, and if you do that, as you can see, it's not just one side that's going to have a constant added. Both sides will have a certain constant added, right? So call this c1, call this c2. So why am I adding only one constant? The thing is, c2 and c1, by definition, they're just some arbitrary constants. So if you take if you take c1 to this side, so if you subtract by c1, what you have on this side is c2 minus c1. Well, that's still just some arbitrary constant, right? That's still just some arbitrary general constant, right? So that's why it's enough to just add the constant on one side. It's enough to just add the constant on one side. So what we get here at last, we're going through some hard work. It's y equals 3x squared plus c. Okay, which is the same thing as what we got before. All right. Now the natural question that should be popping up in your head is, okay, so why did I go through the extra effort and this new method while I could have just taken the antiderivative as before? It's much simpler. It's much less cluttered, takes less space. All cons here and all pros there. So the why, basically the question is why. Well, the thing is, this method actually helps, allows us to solve a much wider range of differential equations. Okay, compared to just taking the antiderivative. And just to give you a good example of this, we had dy by dx equals 6x. Okay, let's just modify that a bit. Let's go down. Okay, so if I say that dy by dx is equal to 6x 6x divided by y. I just made a very small modification here. What's gonna happen now? Well, let's try our preferred method. Let's try to take the antiderivative of the right hand side. On the left hand side, we should get y. We should get y on the left hand side. So we have y on the left hand side. On the right hand side, we have the antiderivative of 6x divided by y dx. I think you can see where the problem is here. Okay, so because we have a y here, we have the dependent variable y here, and obviously we're taking the integral with respect to dx, okay, with respect to x. This cannot be evaluated, right? This cannot be evaluated directly as is. So that's basically where you see the major limitation, okay, of this method of just taking the antiderivative. So the way we should do this actually, as we did here. Okay, so and I want you to pay really close attention to this, because I'm going to later state the general rules for this method, but it's all based on this line of reasoning and logic that I'm going to talk about now. The thing is, what I'm targeting to do is the same thing. It's the same thing as here. I want to collect the y terms, every y term including dy on one side, and I want to collect all the x terms including dx on another side, okay, on the other side, and then I want to take the integral. Okay, so that will work, because if I'm separating the variables, if I'm separating them, I should be able to take the integral. Now I'm not gonna get some, not gonna be blocked like this. So that's why I'm gonna try to separate the variables, and I think it's a title drop. I think you can see where the name of our equations, this particular class of equations came from. But anyways, I'll explain that even more. when I talk about the general rules. So let's try to solve this the right way. So as I said, collect the y terms on one side. So we have dy here. Let's actually let's multiply by dx on both sides. Okay. So what we have here is dy equals 6x 6. Wait, I'll actually write that a bit later. Now we have we multiplied by dx on both sides. Okay, and also what we have here is 6x by y, right? Okay, so as I want all the y terms on one side, the left hand side specifically, let's also multiply by y. Okay, let's also multiply by y. Now what I should get here, okay, the y here disappeared, so I just have 6x, and I have y dy on the left hand side, right? So that's we have successfully separated our variables, okay, as the title says. Now we should be able to take the integral of both sides, right? There doesn't seem to be any problem. So let's actually take the integral of both sides. On the left hand side, what I get is y squared by 2, right? The integral of y with respect to dy is y squared by 2. And on the right hand side, what I get is, okay, so again, this is 3x squared, and plus some constant, right? Plus some constant. Again, as I said, it will suffice just to add the constant on one side. Now this is basically my solution. We can just simplify this a bit. And actually one important thing, two important things. We can multiply by 2, okay, on both sides. So what we get here is y squared equals 6x squared plus 2c, okay, 2c, right? Okay, but again, kind of like the same logic as what I spun just a while ago. C is just some arbitrary constant. So 2c is again just some arbitrary constant. So you can just write it as you have you have a constant c. So this is just some other constant, is let's say c prime, or you could even say d or some other letter. And if you're feeling too lazy, and most professors don't really care about this sort of stuff, you can even just write it as c. Okay, most people wouldn't really mind something like this, because as I said, it's just some constant, just some arbitrary constant. So with that said, this is our solution. And you might be noticing one thing. Y isn't explicitly okay, or very clearly expressed in terms of x. Like y is equal to some function of x. It's not written in that way. This is not in that form yet. Well, the thing is, as I've just said, this is not explicit. This is called the implicit form. Okay, this is called an implicit solution or formula. So this is implicit. And well, for a lot of differential equations, for a lot of them, what you get, the answer that you get at the end, in a convenient manner, is actually an implicit form. Okay. Now, if you're told to, if you're explicitly told to give, write it in the form of y equals f of x, okay, then you should actually write it that way. Like if I'm told to write y as a function of x, actually it's if I want to be really rigorous, it's not exactly a function, it's a relation, okay, or a multivariable function, multi-valued function, you could say. But anyways, I won't get too deep into that. So this is how you'd implicitly express y. Okay, so y is clearly some function or relation of x. So this is the explicit form. Now, as I've said, this you only need to do when you're explicitly, okay, when you're clearly told to find the explicit form. Otherwise, if you're not told to do so, it should be fine to leave it as it is. This is very valid as a solution. Drum roll. There's some reason for congratulations. We did find our solution, right? We did find our solution. Well, okay, so this is how I mean, this is basically the gist of separable equations. Basically, you're trying to separate your variables, okay, and then take the integral on both sides. Okay, so you're this is the gist of it. Now I'll lay out the formal rules for this, okay, and they are, let's see, to the right. Yeah, right here. So these are actually the formal rules for for this method. And again, these are not something to memorize. I you just need to get the hang of things. And these are universally agreed to be the simplest type of differential equations there are. So yeah, let's get right into this. Now, the first requirement is, your differential equation, it has to be first order. Okay, it has to be first order. It wouldn't work otherwise. You can see all of these, these examples I've did, all of them just involve the first derivative of y. All of them are first order. You cannot go any higher than this for your separable equations. Okay, so that's the very first requirement that you need to check. Okay, the second one is, your differential equation. So you have, your first order differential equation. You need to put it in this form. Okay, so some factor, okay, some factor, it might be a, so it might consist of x terms, y terms, both, neither, but anyways, some factor, okay, multiplied by dy by dx, equaling something else. Okay, some other expression. Okay, some expression multiplied by dy by dx, equaling some other expression. So your second step is to bring your differential equation to this form. Now the third step, and this is what the most important one, because this basically determines whether, your equation is separable or not. Okay, to be honest, if you have a first order differential equation, you can, in any situation, okay, in general, force it to be like this. Okay, there's no exception to that. But this is not guaranteed. And this is basically what determines whether you're gonna have, separate, whether your equation is separable or not. Okay, all right. So what you need to check here, it kind of seems intimidating, but basically what it means is, you need to see if you can bring your equation to this form, where with dy you have some function of only y, okay, multiplied with it. Okay, so you have some function of only y, okay, only y multiplied with dy, and this is going to equal dx multiplied by some function of only x. Okay, only x, cannot have y. Okay, yeah, so this is how this is what you need to check, whether you can actually make your equation become something like that. So dy multiplied by some expression or function made up of only y's. Okay, and this is gonna equal dx multiplied by some expression or function consisting of only x. All right, so those are the general rules. Let's actually try our hands at some separable differential equations. Okay, well, actually, first we need to check whether they're separable. But as I think you can guess, for the sake of this video, both of the examples that I'm going to do, they would be. But anyways, okay, the first one that I have on hand is x y prime minus y natural log of x equals 0. All right, so first thing, for separable equations, it's kind of convenient to write y prime as dy by dx. So that's what I'm gonna do. X dy by dx, x dy by dx is gonna equal. Now I'd like to take this to the right hand side. Okay, so this is gonna equal y natural log of x. Now, let's see. Actually, I myself am not following my principles through. Yeah, I should be stating these very clearly, since this is the first time we're doing separable equations. We need to, according to the steps, first thing, we needed to check. We needed to check whether this is a first order differential equation or not. And it indeed is. Okay, it indeed is. You just need to eyeball it. It's, wait, where is it? Okay, you just have the first derivative, right? You just have the first derivative here, so it's definitely a first order differential equation. So step one is definitely a pass. Now step 2 is what you need to have. You need to force your equation to become something like this, right? Dy by dx multiplied by something, okay, some expression, maybe it has x's, y's, or both. Okay, it needs to be equal to some other expression. Okay, some other expression. So we actually have already accomplished that. We actually have, unconsciously even accomplished that. So this is the, this does conform to that. This last step that we need to do, well, actually, we still need to solve it. But anyways, the last one of those 3 steps, which does determine whether this is a separable equation or not, is we need to see whether we can separate the variables. Okay, on this side where you have just dy, okay, can I bring all the y terms? And it seems like we can, right? If we divide both sides by y, what I have here is 1 by y, right? Okay, and also I'm multiplying both sides by dx, so I'll have a dx here. Anyways, what I want to say is if I divide both sides by y, I should have a 1 by y here, but more importantly, there would be no y on the right hand side anymore, right? So we have successfully separated y. Okay, let's see, we can do the same with x, and it seems like we can. We just need to divide both sides by x. Okay, we just need to divide both sides by x. What we'll get is 1 over x, and we still have the natural log here. Natural log of x multiplied by natural log of x, and then we have dx. So voila, we have indeed been been able to accomplish all three of those. So those are all check marked. So this is definitely a separable differential equation. All we need to do is take the integral of both sides and then solve it. Yeah, I probably should have written that as the 4th step. But anyways, that should be pretty obvious. We just need to take the integral of both sides and solve this. Alright, so I'll do that. Take the integral of this side, take the integral of this side. Actually, one thing I'd like to mention is, although it does seem like such an easy or obvious step, a lot of times, it's a common thing in integral calculus. It's not like you can always find the integral of any function, right? So that might be roadblock at this stage. Okay, but let's hope not. Otherwise we couldn't, we wouldn't be able to solve the equation. So yeah, let's see. 1 by y, with respect to y, take the integral of that, you get natural log of absolute value of y. Okay. Yeah, this is if I'm being really rigorous. A lot of textbooks would actually omit the absolute value. Anyways, I'd like to be rigorous with this. And on the right hand side, what you have is, okay, so this one will actually need a bit of work. So what you have is, I'll actually do this on this side. So what you have here is 1 over x natural log of x, okay, dx. Now, if you are noticing, the fact that this is natural log and you have the derivative of it just lying outside, you should be able to deduce that, u substitution is the way to go, right? So if we substitute u equals natural log of x, du is gonna be equal to what? 1 over x dx, 1 over x dx. So 1 over x dx, we have that here, right? 1 over x, and that's also multiplied by dx right here. So that's basically du. So what we have right here is, let's see. So this is going to be du here, and all that we have is natural log of x. But what did we say? That's just basically equal to u, right? That's just basically equal to u. So what we have is u, integral of that with respect to u, that's going to be u squared by 2 plus c. Obviously you have your constant, but anyways, I'll just omit that for now. And yeah, so all we need to do is, u is equal to natural log of x. So this is going to be equal to natural log of, actually yeah, it's just natural log of x. In fact, this is just natural log of x. Okay, I was gonna write absolute value, but I'm seeing that there's really no need for this. Natural log, it was in this form right from the get-go, so no need for that. So what we get right here on the right hand side is natural log of x squared, okay, divided by 2 plus some constant c, right? So I'll add that right here. So this is a valid solution. Okay, this is in an explicit form, as you can see, and this is basically the solution to your differential equation. Now you could put this in actually, did I say explicit? This is an implicit form. Okay, you could put this in an explicit form. Okay, but yeah, I'll already tell you it wouldn't look that pretty. So I think this is much more preferable, especially if you're not directly told to express this as y equals some function of x. You can still simplify this just a bit. Okay, just a bit. It's still possible. Like if you multiply both sides by 2, what you get is 2 natural log of y. Actually, this is actually pretty neat. You know, you have 2 natural log of y. That basically means, you know, if you take the power here, okay, you know, log rules, well, absolute value of y squared, and if even if you just took y squared, they're both the same thing, right? You're squaring. So this is actually, okay, this is actually pretty interesting, pretty interesting. I'll actually erase all of this. You get here, you get natural log of y squared is equal to natural log of x whole squared plus, you know, 2c, but that's just some constant, right? So I'll not bother with, you know, c prime or d or k or anything like that. I'll just write c, you know, just as it is. So this is basically your solution. This is basically your solution. You can still, you know, you can still kind of nudge it to kind of just a bit more simplified form. To be honest, I don't know whether this, you can call it more simplified, but you know, you can subtract c from both sides. It's still basically just adding some constant, right? And you know, when you add, you know, when you have natural log of, you know, c plus natural log of y squared, oh no, this is basically gonna be equal to, according to our log rule, some constant c. Again, I'm actually I'll just write k here, but anyways, it really doesn't matter. Again, it's just some constant, okay, some constant k multiplied by y squared, all that inside the natural log. So this is you could say the most concise form that you can get, with this equation. So I'll write k here. So natural log of ky equals natural, oh, no. Natural log of ky squared equals natural log of x whole squared. So this is as concise of a form for this, this solution that you can get. One thing, and I'd really like to warn you about this. The thing is, a lot, you know, it's very tempting. It's very tempting. Take the power of e on both sides. So it's like, you know, ky squared equal to e to the natural log of x squared, and by instinct some of us might even write x squared, you know, e to the natural log of x, log of x, that would be x, and you know, if you square it you get x squared. This is not correct. This is not correct, okay. You know, I might be visiting some really elementary stuff right here, and you might hate me for this, but we really need to be very careful about this. It's a fact that if you know, a to the power b, and you know, if this is the whole thing to the power n, this is in fact the same thing as a to the power, you know, b multiplied by n. Okay, you can just write it as bn. But okay, so these two are the same thing, but this is not. And I repeat, this is not. These two are not the same thing as, you know, if you have a to the power b and b to the power some n. Okay, so this power isn't on the whole thing. No, not that. It's just on the b itself, and this cannot be simplified anymore. Okay, this cannot be simplified anymore, and certainly not the same as these two. Certainly not the same as these two. So this, you know, even if we took the power of e on both sides, this wouldn't simplify anymore. Okay, this wouldn't simplify anymore. Okay, so just need to be careful about our basics. All right, so I'll leave it like that. Our, you know, our solution, I'll leave it like that. It should be okay. Now, with that one done, let's actually jump right into another problem. This one will be just a bit more involved, but still, again, you know, it's all our basics. Let's I'll actually scroll to the, yeah, I'll scroll to the bottom. Okay. So let's see what we have on hand here right now is, let's see, um, 2 2 y prime, secant squared of y, it's gonna be equal to sine of x plus y, sine of x plus y, minus sine of x minus y. I'll need to scroll to the right. Maybe should have written it a bit smaller. Sine of x minus y and plus 2y prime, plus 2y prime. So this is basically our equation. All right. So again, you know, we should do all our checks. Okay. First thing, need to verify that this is in fact a first order differential equation. It seems like it is. The highest part, you know, the highest derivative you have is, you know, the first derivative, and you know, even here you have the derivative, but again, it's the first derivative. So the order is in fact one. It's indeed one. So that one we got through. The second thing to do is, you know, collect the dy by dx, collect all the dy by dx on one side. Okay, so you need to put it in this form, dy by dx multiplied by something. Basically you need to collect it on one side on and discard, or just dump everything else on the other side. So that's what we're gonna do. Collect all the dy by dx's, okay, on one side, and just discard everything, just dump everything on the other side. So if we collect y prime on this side, okay, dy by dx, we get here is, okay, so subtract 2y prime, okay, 2y prime from both sides. So we get here is 2y prime. I'm subtracting 2y prime, and we also have 2y prime here. We can actually factor this. So if 2y prime multiplied by secant squared of y minus 1, right? Okay, so I subtracted 2y prime. So this is really the same thing. So I've collected the dy by dx on one side. Actually should have written that as dy by dx. Anyways, we'll get time to do that anyways. So this is your left hand side. On the right hand side, as I said, you just dump everything else. So do you have here, okay, it's already on the right hand side, sine of x plus y minus sine of x minus y. Now different people have different preferences of simplifying this. If you're a fan of directly applying the formula, if you remember the formula of sine of a plus b, sine minus sine of a minus b, you can just do it directly. There's no problem with that. You'll get the simplification pretty easily. But if you're not a fan of doing that, it's still fine. Okay, let's just walk through this. So this is, you can expand both of these. You can expand both of these terms using our angle addition formula, cosine angle addition formula. So this is this one is gonna be sine of x, cosine of y, plus sine of y, and multiplied by cosine of x, right? Multiplied by cosine of x. Okay. Now this is and this one right here, the other one right here is gonna be it's about the same thing as this. If you remember the addition formula, you just get a minus in between. So this is just gonna be sine of x cosine of y minus sine of y cosine of x. All right, but we are subtracting this, right? We're subtracting this, okay, from the other one. So we're subtracting this. So what we see here is sine of x cosine of y minus the same thing. So these two cancel out, and sine of y cosine of x minus minus plus again the same thing, sine of y cosine of x. So on the right what we're gonna have, I'll choose a different color. Yeah, let's actually progress on both sides. On the left we have 2y prime, wait, again I'm gonna do the same thing. No, this time I'll write dy by dx. Okay. Oh yeah, and one last thing, secant squared of y minus 1. What's that? We know basic trig formula. This is equal to tan squared of y, right? Tangent of y squared. So 2 dy by dx tangent of y squared, Okay, well, that sounds wrong. Tangent of y, tangent squared of y. I guess that's the way you need to say it. Okay, so this is going to be equal to 2. Let's see, sine of y, 2 sine of y cosine of x, right? Cosine of x, right? Let's just check if that's correct. Yeah, so that's the factor that survived. So 2 sine of y cosine of x. Well, we have 2 on both sides. We can just cancel that out. So 2 is gone. Okay, so we have successfully brought the derivative y on one side, multiplied by some factor, okay, and everything else is on the other side. Now last thing we need to check is whether we can collect the y terms, okay, everything y related, including dy on one side, okay, dy as a dy multiplied by some expression of y, that should be equal to dx multiplied by some expression of x. So let's see if we can do that. Well, it seems pretty simple. All we need to do is multiply by dx, so that this goes to this side, okay, this goes to this side, dx, and also if we divide by sine of y, then this is going to disappear from here, and you'll have all the y terms here and all the x terms here too. So that should work. Okay, that should work. So what you get here is, actually I'll just expand it for a moment. So you have sine squared of y cosine squared of divide by cosine squared of y. We are dividing by sine of y on both sides, so it's the same as multiplying by 1 over sine of y, and we have the dy and we have the dy. This is going to be equal to, on the other side, what we have is just cosine of x, dx, right? Just cosine of x dx. Those are the only x terms, okay, in this equation left. Now we can simplify the left side a bit. Now, one thing is the sine of y cancels here. You have power of 1 here. Okay, so sine of y cosine squared of y. I'll just actually do some work on here. Okay, so this is the same as sine of y cosine of y multiplied by 1 by cosine of y. 1 by cosine of y, right? Okay, so I just split the fraction. Now, sine of y by cosine of y, that's just equal to, tangent of y. And 1 by cosine of y, that's just equal to, whoops, not cosine, that's not cosine, secant of y, right? Secant of y. Now, we can just put that right in here. So we can just plug that right in here. This is going to be equal to, our equation is tangent of y, secant of y. I think you see why I did that simplification. Okay, is this dy. This is going to be equal to cosine of x dx. Okay, now it should be pretty simple. All we need to do is take the integral on both sides, right? So we should take the indefinite integral or the antiderivative on both sides. Now, integral of tangent of y secant of y, that's just equal to secant of y, right? Secant of y. Okay, and I'll add the constant on the right side. So the integral of cosine of x is just sine of x. So it's sine of x plus some arbitrary constant. So voila, this kind of complicated looking expression, equation, especially since it had sine of x plus y. So it's kind of like x and y are both bound inside the signs here. This kind of slightly intimidating looking thing, this equation, which probably in the first video, if you just came here after the first video, just from that, this one would look like kind of like an impossible equation to solve, right? This should look like that. If we just stuck to taking antiderivatives on one side, that it should definitely look very intimidating and impossible. But as we saw, using using our logic and reasoning of separable equations, separating the variables, we were able to solve this, and it's a pretty neat solution. And actually, my bad, but I actually forgot to add one thing. There is an initial condition for this problem, and the condition is that y of 0 is equal to 0. So, and again, this is a first order equation. We need it to be a first order equation, and for these, to find a particular solution, you just need one. You always need just one initial condition for these. So let's use that condition. So when x equals 0, I'll switch color. So when x equals 0, on this side, what you have, sine of 0, so that's 0 plus c. This is going to be equal to, y is also 0, right? When x equals 0. So secant of 0, or basically 1 by cosine of 0. Since cosine of 0 is 1, and 1 by 1, you basically have 1 here, right? So c is 1. So your final solution, we really deserve a pat on our backs. This is going to be equal to secant of y is equal to sine of x, the sum not some constant, what I was going to say, we know that some constant is 1, right? So this is my particular solution, okay, that also satisfies my initial condition, and this is basically, at the very least, it's an implicit form of our solution. I really personally don't have any motivation of making this explicit, and we are not told to do so that either, so I'll just leave it like that. So one last thing, I almost forgot to do that thing. As I said before, if some of you are, in fact, and it's not really a bad thing at all, if you're dissatisfied about the fact that these, we had some loosey goosey logic when we multiplied by d. Where was that? We had some loosey goosey logic when we multiplied by dx, especially when we just hung an integral sign on both sides. Okay, if you're dissatisfied about that, and as I said, it's really not a bad thing. Rigor is a good thing, to be honest. Rigor is a good thing. It works because let's just see why it works. So the thing is, a separable equation, as we said, it has to, it has to fulfill, it has to eventually come to this form, right? If it is in fact a separable equation. Well, the thing is, we got dy and dx on the, on the opposite sides from a statement before. So if this is your, if this is the statement you got at the end, the one before, okay, before we did that kind of loosey-goosey multiplication, is in fact this one. And until so far we haven't, we wouldn't have done anything that, is kind, it's kind of not rigorous. Okay, so until so far we're good. Okay, until so far we're good. As I said, this we need to be able to get to this far, okay, for it to be a separable equation, and no breach of logic so far. Now the thing is, what I'm saying, this basically means that m of y, okay, m of y multiplied by dy by dx, this is some function, some expression or function. This is equivalent to, equivalent to n of x, right? N of x. So if two functions are equivalent, there's no problem if you take, the indefinite integral of both sides, okay, of both sides. So if you take the indefinite integral of both sides with respect to some variable, okay, with respect to some variable, and the one I'm interested in is definitely x, okay. So there's actually, unlike before, we are not doing anything wrong here, we're not doing anything loose here, you could say. It's completely valid, since I said my two functions are equivalent, these two expressions are equivalent, I can very easily take the antiderivative of both expressions with respect to some some variable, and obviously we're going to use x here. So this is all fine and well. The right hand side is what you'll get, even if if you did the loosey goosey logic. So we're good, we have achieved what we wanted to on the right side, okay. This is fine. The left side is what concerns us, okay. So how do we get to, how do we get to something like the integral of something with respect to y? Well, the thing is, again, you have some function of y. Actually, it's better to write it as, integral of some, m of y, but y is some function of x, right? Y has to be some function of x, okay. And this is multiplied by the derivative of y. Derivative of y, that's just lying outside. Then you have dx, and you should be able to recognize this pattern, okay, whether by use substitution or by the reverse chain rule, you should be able to recognize this pattern. This is just gonna be equal to, m of y, okay, m, the function of m, with y as the variable, and the integral of that with respect to, this function right here, which is y, okay. So this is basically, the reverse chain rule, okay. This is basically the reverse chain rule. I hope you have seen this, or at least remember this before. So this is that, as I was trying to say, that is why our method works, okay. There's no leaks or flaws or gaps anywhere. You can show it formally that our method for solving separable equations really does work, okay, really does work in the highest rigor and form. But anyways, so that's the end of this video. Yeah, there's definitely nothing more to discuss, and I'll see you in the next one. Study smart. And if you like this video, and if you appreciate it, please do leave a like, and please subscribe and keep supporting this channel. So yeah, again, study smart.